Good morning, everyone. Thank you for coming. I hope you're enjoying the conference. This is my first talk at the conference. I have another 3, including a workshop, so you're definitely welcome to join. There's a bunch of different topics, but today's is about C++. So I hope you are C++ developers. Could you raise your hand, please, if you're working in C++? Okay. If you're not, I hope you'll see that C++ is really a more modern language than it has a reputation for being. But still, I assume sort of some fundamental knowledge of C++ for this talk. My name is Sasha Goldshtein. I live and work in Israel. Hi, thank you. Yeah, so let's just get started. I work at a company called Group. My contact details are at the last slide because the conference template doesn't have room for all the contact details on the first slide, and I really try to use the template provided. So, in this talk, we'll talk about the C++ 11 compiler language support, which compilers support what. I assume from past experience that most of you work on the Microsoft platforms, Windows, Visual Studio, but even if you're not, C++, as you know, is a portable language, and so Thank you. And so there's a bunch of compilers that implement the standard completely already, and you can use them on Microsoft platforms like Windows with Visual Studio, and you can use them on Linux with GCC or CLang or whatever. We'll also talk about the best practices for modern C++. When I show you features of the language, at least for the major ones, I'll try to show you how to use them correctly. And finally, we'll also talk about what's up with C++ 14, which is the upcoming standard, the revision of the C++ 11 standard, which is supposed to come out in 2014. And it's pretty final. There's a final draft that's being approved in the national language committees, and it's probably going to be approved in a few months. And so we'll have yet another standard to learn. The good news is there's not very many new features in C++ 14. They only had 3 years to revise the language, so I'll show you a couple of them at the end of the talk, and if you're interested in more details, there's a bunch of great resources online. And finally, we will not be able to cover every language feature in C++ 11, notably variadic templates, which is a really lovely feature, but a very complex one, is something I won't have time for today. And again, I refer you to the internet, to books, to a bunch of reference material that I'll be happy to share with you afterwards. So let's get started with the C++ 11 compiler support. C++ 11 was released in September 2011, and so Visual Studio 2010, 2012, and 2013 incrementally support more and more features of the standard, but even Visual Studio 2013 does not yet support everything. And that's 2 years after the standard has been released. The Microsoft plan is to issue incremental quarterly updates that support more and more features in the standard until eventually they reach complete coverage of both C++ 11 and C++ 14. So they're going to do it in stages, and eventually in a year, 2, 7, cover everything in the new standard until there's a next new standard to cover. However, the 2 major features that I'll be talking to you about, which are lambda functions and R-value references, are available in Visual Studio 2010, which was released before the standard was finalized, which is sort of impressive, at least for Microsoft. They usually tend to lag behind in standards implementation. Other compilers like GCC, CLang, Apple's LLVM port, they pretty much support everything in the standard right now, as they have for a couple of years now, and they also support some of the C++ 14 features. So again, if you want to test out the new features which haven't even yet been approved in their complete final shape, you can use other cross-platform compilers to try them out. There's also a bunch of online C++ compilers to play with. If you're learning a new feature and your favorite Visual Studio version doesn't support it yet, you can open up a browser, type in a C++ program, and run it with input and output and see exactly how that feature is supposed to behave. There's a link down here to a comparison chart between the various Visual Studio compilers, as well as a couple of GCC versions, which shows which version implements exactly what. You should note one thing though, a compiler might be mentioned in this chart as say, we implement R-value references. But there's a bunch of different revisions to the R-value references features in the C++ standard. So you might also see stuff like, we implement R-value references revision number 2. we implement our value reference as revision 3.2. And so even within the standard, you have the standard has evolved over more than 10 years, and so there's a bunch of different ideas of what a certain feature's implementation is supposed to look like. And I think I'll show you a couple of examples of this later. I'll mention a couple of features which are not implemented in 2010, even though it theoretically has support for that feature, and were added later. So that's for the compiler support. And let's just get started with our first little feature in C++ 11. By the way, people in Israel are really impolite, so please feel free to interrupt. I'm used to that completely. Feel free to ask questions, interrupt at any time. And of course, you're welcome to come and to discuss anything you like after the talk.
Just one quick
Yes, please.
I presume the individual studio versions Microsoft isn't packaging those features into the older versions, version 2013 or 2012.
Yeah, so the question is Microsoft backporting features to older Visual Studio versions? No, they're not. You can still use, if you're using Visual Studio 2013 and you have Visual Studio 2010 installed, you can use 2013 with the 2010 compiler. But you can't do it the other way around. So basically, if you want the new language features, you have to use the newer compilers. Okay, so let's take a look at auto variables. Auto is a keyword which was actually part of C++ for years. It was a standard feature of C++ 98, but no one used the auto keyword really. It was specific for a declaration of local variables which would be assigned register or memory storage by the compiler. Again, no one really used that feature in older versions of C++, and so they repurposed the auto keyword for something a bit different. It still applies to local variables, You can declare local variables using the auto keyword, and the compiler will deduce the type of that variable from the initialization expression. So you can say things like, well, I have a map of int to a std list of int, of string, which is a pretty complex STL data structure. And so what exactly is the type of the begin, which the begin function would return? So it's a map iterator in a map of int to std list of string, which is a pretty long expression to type out. And so if the compiler can deduce what the variable's type should be, you can just omit it and say auto. Now this is a compile time feature. It's not like, VB6 used to have this variant keyword, or JavaScript have objects. No, it's not anything of that sort. It's completely statically typed. The type of this iter variable is determined at compile time. You just don't have to spell it out. That's the whole difference. And so the compiler can deduce from the right-hand side what the type of the local variable should be. In this kind of situation, it's just a matter of productivity. You don't have to think about the actual type of the initialization expression, and potentially you could change that type a little bit later, and you won't have to modify the local variable declaration. But there are some situations, which we might see later, in which you can't really determine the type, the compile time type of the local variable. You have no way of spelling it out, even if you wanted to, and that's the case with lambda functions. And in these situations, auto is the only way of declaring a variable of a specific type. And because the type is really unknown to you, you can't spell it out, only the compiler knows the precise type. Yes, please. Welcome. Good morning. So this is one example. Another example which goes on and complexifies this thing is, let's take this iter thing and then make a pair of iter and whatever the key range function of the map would return. If I really wanted to spell out the type of this pair local variable, it would probably go out the screen, go off the screen. And again, the compiler really saves me some typing here. It deduces the type of this pair local variable from whatever appears on the right-hand side of the expression. And finally, there are a couple of situations where this feature simply does not work, or I think you should not use it. One of them is if you use this ternary conditional operator. So if you have an expression like ptr equals condition, and then new class 1 or new class 2, the compiler does not have a way at compile time of deducing the left-hand side's type. It could be class 1 or class 2, depending on the value of the condition, and so the compiler would simply bail out with an error here. Even if class 1 and class 2 have a common base class, it doesn't matter. The compiler requires that the right-hand side expression have type that can be determined at compilation time. You can obviously apply a cast to this whole thing on the right-hand side, but then, I mean, why bother if you're going to write out the type anyway? And finally, you can also do stuff like this. Auto x equals 15, or auto s equals cast to string of the literal string hello. And again, I mean, you could write this. It is legal C++. You will see people use C++ that way. I don't see why. I mean, it's not shorter, it's not clearer, and in this particular case, with the S declaration, what happens if I omit this cast to string? What's the type of S going to be? Yes.
In the left one where x equals 15, what sort of integer would it give you?
Right, so before we go to S, yeah, what's the type of X going to be? Where 15 actually has, I mean, it's a literal, and literal numbers in C++ do have a type, and that's int. If you want a long, you can append L to that. If you want a double, you can append a dot, but I mean, this thing is an int.
It's also 4 bytes sign.
4 bytes, yeah. But here, if I don't write out this cast to string, what kind of S would I get? Probably a char star or a const char star, yeah. Not a string, not a standard library string. So again, this looks pretty pointless. I mean, why not just initialize a string and say it's going to be a string? So again, this is legal C++. I do not encourage this. I'll show you some bad examples, some additional bad examples in a couple of slides.
Quick question on the iterator. Would that return a const iterator, or can you have a choice? I can't remember whether you just get a const iterator or whether you can change.
Yeah, we'll get to that.
Okay.
There is a very handy feature for iteration, which is the range-based for loop. And so, and I'll show you exactly how it maps toward yours. So the range-based for loop is another small feature of C++ 11, which is supported by all the compilers, including Visual Studio again, and it just provides you automatic iteration over virtually anything that has a begin-end function pair. So you can use this for arrays, you can use it for vectors, for lists, for maps, for any STL container, and you can use this with your own collections as well if you overload the global begin and end functions. So the C++ standard adds global std begin and std end, which you can overload or actually specialize. These are template functions. You can specialize them for your container, and then you also get support for this range-based for loop. What does the range-based for loop look like? Well, suppose I have an array of numbers. I can say for int n colon numbers, and that I usually read this as int n in numbers. I can just use this n, and it will have it's the iteration variable, which will get the numbers from the array on each iteration. So I don't have to worry about the size and shape of that array. I don't have to worry about calling begin and end and using an iterator. If the size of this thing is known to the compiler, then there's a couple of overloads for this begin and end global functions, which the compiler can call, get an iterator to the beginning of the array and to the end of the array, and so the iterator is really hidden here behind this nice syntax. Now you can also do things like this. So suppose I have a map of std string to a std list of int, which again is pretty nasty to write out. I can iterate this thing in steps. So first, I want to go over all the pairs of string to std list of int, which I have in this map. So I use a range-based for loop, but here, instead of just writing out the pair type, I can say auto. And I can also add specifiers to this auto thing. I can say const auto, or const auto reference, or auto reference. And this will affect the type that I get out of the iterator. So in this case, the pair value here, which I get on every iteration, is going to be a const reference to a pair of string to list of int. And why do I insist on using a reference here? Why not just auto, which is going to be a value and not a reference? What happens if this pair thing is a value that I get out on every iteration? There's going to be a copy, right? And it's going to be an expensive copy because I'm copying a pair of a string, which has to be copied, and a list of ints, which could be potentially quite big, which also has to be copied. So by using the reference specifier here, I can control exactly the type of variable I'm going to get. And I'm using const here because I really don't intend to modify this pair. I only mean to read from it. If I wanted to modify the pair, like maybe adding something to the list, I could use just auto-reference here without the const specifier. So I have some control over what I get out of this range-based for loop thing. And then finally, once we have that pair, the second element of the pair is a list of ints, and so I can iterate that again using the range-based for loop. This is really nice. I mean, it saves a lot of typing. You don't have to worry about iterators and declaring iterators. You just get the compiler to spell this whole thing out for you. Does it make sense? Now again, you can use this with your own collections. So maybe you're using MFC, or maybe you're using some collection library that you developed. So all you need to do basically is just specialize the begin and end global functions in the std namespace for your collection, and then return a begin iterator and an end iterator, like you probably already do, from these global functions, and then you can just magically use the for loop with your own containers. Okay, the last feature in this introduction before we get to Lambda functions, which is again a small feature, is called initialize lists, or uniform initialization. And I'll explain why it's called uniform initialization in a moment. So basically, initializer lists give you a handy syntax for initializing collections of stuff without, calling a bunch of methods. You could already do this with arrays in C++, whatever, in the 90s. You could initialize an array without calling methods to initialize each element using curly braces, right? So you can now do this with vectors, with lists, with maps, and of course, again, with your own classes, because there is a way to extend this syntax to your own classes. So first, let's take a look at the vector. I have a vector of ints here. I want the numbers 1, 2, 3, 4 in it. I just use curly braces like this, like I could with an array. Or I have a list of strings here, and I want a couple of strings in it. I can use, the equal sign here is really optional. It's exactly the same thing. And again, I use curly braces, and inside, I don't even put strings. I have const char stars, I have literal strings, but it's fine. The compiler is gonna invoke the conversion to a string for me and insert them to a list. So this is really much easier to initialize static collections like this, and you can add this to your own containers, or you can even use this to initialize your own classes, which aren't really containers at all. And this is why it's called uniform initialization. You can use it to initialize containers, but you can also use it to initialize whatever, any class basically that has a constructor. So let's see a couple of examples. Here, my count is a container, which we'll show in a couple of seconds, and I initialize it with the curly braces exactly like a vector. And the idea here is that I'm putting some numbers in the container. The second example here, with the point class, the point isn't a container, and I can still use curly braces to initialize it. So this will just invoke a constructor which accepts 2 integers. That's all there's going to be. And now the myContainer class, to accept an arbitrary list of numbers, has to do a very simple thing. It has to provide a constructor which takes and std initializer list of int. And this initializer list is a magic compiler thing that the compiler will initialize for you and pass it to your constructor. And then you can iterate over this and get out all the elements provided by the user. So you don't have to use ... You don't have to write variadic functions which take an arbitrary number of parameters. You just use initialize a list of something, and the compiler is going to pass in a thing like that to you. So again, this is uniform initialization because you can initialize anything with this curly braces syntax. You don't have to use regular parentheses, regular braces for classes and for constructors, and curly braces for arrays. You can use curly braces for everything. And again, naturally, some people will take this to the extreme. And so this is my next slide. Taking it to the extreme looks, at least in my opinion, like this. It would say stuff like, well, I want a d-word variable, and I want to use uniform initialization, So I go ahead and type auto flags equals dword curly braces file flag no buffer. I mean, it's legal C++ and all. It looks a little extravagant to me. And then auto numbers equals std vector of int curly braces 1, 2, 3. What did we gain here by using auto, really? Again, it's legal C++, but why? And probably the most extreme example is over here. I want a handle to a something, like an event, and I don't want to initialize it. But I still want to use the curly braces, right? So I can type in auto event handle equals handle curly braces without anything in the braces. This compiles. This will give us the default value for a handle, which is null. Again, I really don't see why. And the cool thing, sort of, is that you can use auto with function return types as well. You can declare a function which returns auto. Thing is, the compiler will not deduce the return type for you in this situation. You still have to specify it using this trailing type syntax. So you can declare a function which returns auto, but really it returns bool, which is specified down here with this error syntax. This doesn't look like C++ at all anymore, right? I mean, I think Pascal used to have this trailing return type declaration syntax. So again, you can do all of this in C++, and you will see code that uses these conventions, because some people think it's good to have everything done uniformly. So you can have uniform initialization with curly braces. Great, let's use it everywhere. You can declare all your variables using auto. Great, let's declare all my variables using auto. This is what I think of this. So anyway, these were 3 little features of the C++ standard: auto, the range-based for loop, and uniform initialization, which you can really go ahead and use in your code right now. They are all supported in Visual Studio today. Initialize the lists are only supported in Visual Studio 2013, but the range-based loop and the auto are supported way back. So the major feature we're going to be talking about is lambda functions. And this is legal C++ now. And it uses this new lambda function syntax, which I'll be showing you in a second, which really begins with these rectangular brackets over here. So basically, this main function declares a lambda function which takes no parameters and returns nothing, and calls that lambda function. And these 2 lines are identical, and again, I'm going to explain them to you. So the motivation behind lambda functions is that you can now inline a method or a function inside another method or a function. If you've used lambdas in JavaScript, Python, C#, any other language virtually, the idea here is very, very similar. You declare a function inside another function, and then you can call it directly, or you can pass it to someone else. So here's one example. We have a list of ints, and now we want to call some STL algorithm, like for each of those ints. And what I want for each to do is to print every int I have in that list. So I can declare a little function over here called print none, and this is a local variable. It's not really a function per se. And I initialize it with this interesting syntax. This is a lambda function right here. And so it starts with these rectangular brackets, and then I have a parameter list for my function, but it doesn't have a name. It only has the parameter list. And then I have the function body in curly braces like always. And so this thing here is a locally declared function which takes an int and prints it out to the standard output. And once I have that, I can pass it to STL algorithms which expect a function object, which expect something that can be called like a function. So we could pass a real function to the for each algorithm, or we could use a function object that we spell out explicitly, a struct with an operator for function call, or we could use a lambda function like this. And you don't really have to declare a variable, of course. You can inline the whole thing. So this thing here could just be this expression. Another example, suppose I want to find the number of even numbers in that list. So again, I use the COUNTIF STL algorithm, which is pretty useful. It goes over a range and tries to evaluate a predicate for each element in that range, and then returns the number of elements that match that predicate, that match the filter. And so the filter here is this, a lambda function that takes an int and returns whether that int is even or not. So this is another example of just inlining a little function instead of going to the global scope, writing a function or a function object, and then passing that in. And finally, a third example with the transform STL algorithm. The transform algorithm is a bit more complex in that the lambda function has to take a value in and produce a different value, potentially of a different type, out. In this case, I use transform to take the elements from this list of ints and return their squares and then print that to the standard output. So I use the ostrim iterator. That's not really particularly interesting. The interesting part again is the lambda function down here, which takes an int and squares that int. Okay, so let's take that for a spin in Visual Studio for a second. I have this function I worked really hard on called integrate. Are the fonts big enough for hearing back? Yes? Okay. So I have this function here called integrate, which is a template function which takes a function as a parameter and then tries to approximate its integral within a certain range. And the idea here is that the function itself is a template parameter, so I can pass in anything that will have the function application operator available, which I can apply a function called to. So this will work with a function, this will also work with a function object, and this will also work with a lambda function. So I have here a to-do task for myself. Use the integrate function to find the integrals of x squared and of sine of x from 0 to 1. So let's try this. I'm going to integrate, and then the function is going to be right here. From is going to be 0, to is going to be 1, and the number of points I want to use for the approximation is 100. So first, we need a lambda function here to return x squared. This is pretty easy. So I declare a function which simply returns x squared using this, say, very familiar syntax. And this is going to return the integral. Let me print it out. And then we want the same thing with sine of x. So this is easier because I can actually pass in the sine function from the standard library. From 0 to 1 over 100 points. So the reason I'm showing you this is that I can, hold on, something's not quite compiling here. Of course, not F, it's called integrate. Right, so the reason I'm showing you this is that I can pass in an actual lambda function. I can also pass in a function from the standard library, which is a global function. Now this probably does not compile because I don't have, oh yeah, well, it says the following. Cannot determine which instance of overloaded function std send is intended. And the reason is that send has an overload that takes a double and an overload that takes a float. And probably also an overload that takes a long double. So I really can't use it like this. And I could, of course, specify the type name of the function explicitly because I'm calling it template, but it's probably just going to be easier to do this. Again, use a lambda function here and return the sine of x. Okay, so this thing hopefully compiles, and now we have a couple of reasons for using lambda functions. One is simply when the function is not available anywhere, and the other is when the compiler cannot determine the particular overload that I want to pass in to another function. This was not intentional, by the way, but it really did work out. Okay, so we have a couple of examples for really simple lambda functions. Let's take a look at a more complex situation. So what I want to do down here, and I'll need to go back to the slides for this, is the following. I want to ask the user for a natural number, and I'm defaulting to 17 if the user didn't provide anything interesting. And then I have this function object over here called filter divisor, which has a Boolean operator function call, which takes an int and returns whether that int is divisible by divisor. Now the thing about this function object here is that it's really not just a plain global function. It's a stateful function. It has to store in it the divisor which the user provided, and then the evaluation of the function call operator depends on that. So I couldn't write this thing as a global function unless I wanted to use global variables as well. And it's also unclear how I can use the same function object with a lambda function, because it has to take state from the outside. It has to take that divisor provided by the user as input. And so here's how it works. We have syntax with lambda function for capturing external local variables. So a lambda function has access to local variables from its enclosing scope. And again, pretty much every other language that has lambdas has this feature as well. In C#, for example, this is implicit. You don't really have to use new syntax to capture variables. In JavaScript, it's also implicit. In Python, it's also implicit. C++ really goes the hard way here and forces you to think about whether you want to capture external locals or not. And if yes, whether you want to capture them by reference or by value. So here are a couple of examples. I have a lambda function here called next step, which calculates the next Fibonacci number. And so we're starting from 1 and 1. These are local variables in the enclosing scope. The lambda function itself starts over here with these curly braces. And it wants access to the fib1 and fib2 local variables from the enclosing state. And so this little ampersand over here in the brackets says, I want to capture every local variable I need by reference. So I can modify them from within the lambda function. And so here I basically just do a swap and move on to the next number in the sequence. And so this ampersand gives me the ability to capture local variables by reference. You don't always have to do this. I mean, you don't always intend to capture stuff by reference. Capturing by reference does give you the ability of modifying external local variables, but maybe you just want them in as input. And so you also have syntax with this equal sign in the brackets, which captures by value. And so here, instead of capturing by reference and letting me modify external local variables, if I use the equal sign, I can only read the external local variable that I passed in by value to my lambda function. And so I can mix and match as well, by the way. I can say, I want this variable to be captured by value, I want this variable to be captured by reference, so I can be really, really explicit about it. And again, as always with C++, the idea is performance. If you want to capture something by reference, you're not going to copy it, so you save a little time on copying. On the other hand, you can now use a lambda function to modify local variables from the enclosing scope, which could be a little dangerous. So this is the C++ trade-off all over again. You can be dangerous if you need it for performance. And so in our particular situation, I want to rewrite this thing to use a lambda function. Right now, it uses a function object over here. This thing over here is a function object, and I mean, ignore the rest of it, but this is a function object which uses this filter divisor struct over here on the top. And so I have to find a way of replacing this struct, which takes in some state and stores it inside, with a lambda function that also takes some state from outside and stores it for the function application operator. And so the way we're going to do this is the following. The function itself takes an unsigned int, and what I wanted to do is to return whether n modulo divisor is equal to 0. But again, I get an error here. And the error is an enclosing function local variable cannot be referenced in the lambda body, and the sentence goes on, unless you use one of these special operators to indicate how exactly you want to capture it. So I can't just gain access to a local variable unless I say whether I want to capture it by reference or by value. And so in this case, I can definitely capture it by value. I'm not modifying this variable, I just need to read the value provided by the user. And so now this thing over here is pretty equivalent to this function object over there, but of course it's much less verbose. It's all just a single line, but it's functionally equivalent. It will generate, the compiler will generate a function object which takes in this local variable and stores it locally, and then the function application operator will use that internal variable over and over again. And it's also very efficient because in the release build, this whole thing can be optimized away. I mean, this struct or this single line over here, which is equivalent to the struct, these functions are inlineable. The constructor here can be inline, the operator, the function call operator can be inline, so this whole thing can disappear if optimizations are turned on and be replaced with a couple of assembly instructions. So this isn't less efficient than using a global function or writing out the code by hand. The compiler still has all the optimization opportunities. And I'm saying this because in .NET, for example, in C#, Lambda functions are treated as function pointers. And the compiler cannot inline a function pointer through a function pointer. Here, it's not a function pointer. It's a function object with a standard function call which can be optimized by the compiler. Okay, so this is an example of applying this capture by value operator. Let's take a look at another example of using lambdas. Well, this is a cute example that I just want to show you, even though it doesn't add anything new. I have here a vector of customers initialized using the uniform initialization, list initialization syntax. Of course, customers are not const char stars, but they are convertible from const char stars using a constructor. So I can initialize a vector of customers like this. And then I want to sort this vector by the customer's city, which I haven't actually specified, but let's assume that I have. And so I want to do something like this. I want to sort this vector from the first element to the last one, and I want to use the overload of std sort, which takes a predicate that says how to sort the elements, or more specifically, how to compare two elements. Let me just scroll this thing a bit. And so I really need a lambda function here, which takes two customers and compares their cities and returns returns which one is bigger, basically. And so we're going to do this like that. I'm going to take in a couple of const customers, const references to customers, and I'm going to return whether a.city is bigger than b.city. And so we have now successfully sorted this vector by the customer city, assuming that the customer city, was obtained from somewhere, like a database maybe. And so std sort really requires just this predicate, really simple predicate, and we have provided it with one. No need for external state in this example. We're just writing a global function. And finally, one more example over here. So here we're told the following. Write a lambda function that doesn't take any parameters, but every time you call it, it will return the next prime number starting from start, which is a local variable in the enclosing scope. And the code below attempts to use this function, but will always print 43. So we have to modify this f to behave a little differently. It has to start from start, find the next prime number and return it, and then when we call it again, find the next one and return it, and so on. And again, this is just an example of using capture by reference. I want to capture this start local variable by reference and mutate it as the lambda goes along. And so it will be something like this. While not is prime start, let's increment start, and then finally we want to return start and move it forward by 1. And the thing is that start, again, is a local variable from the enclosing scope, so I can't modify it like this unless I use the reference capture operator in this reference over here. So we have now captured start by reference. And so after this loop, if you look at the value of the start local variable, it will have a different value. main and this start and this f lambda, they see the same variable, so there's the same local variable that's shared to two different functions. It's a bit weird, but it's very useful. So let me just compile this, and then I want to bring us to the return statement over here. So as you can see, start has indeed been modified to 618, which is one past the last prime number that it printed out, which was 617. So this thing really worked. And we have an example of using capture by reference as well. So these are lambda functions, more or less. Any questions about lambda functions?
How does it fit in with unit testing in terms of, because you're capturing a lot of functionality effectively in your code, but it looks simpler in your code, but you still want to test your code, don't you?
You still want what?
You still want to test your code. Does it potentially make your code more complex to test?
I don't think so. I mean, why? Let me say this. Lambda functions are very, very useful when you're going to write a one-off function that you're not going to use anywhere else. Obviously, if you find yourself writing the same lambda function 15 times, it's probably a good case for reusing it as a global function, as a function object or something. But it's pretty common, especially if you're using the STL a lot, that you need these one-off functions, like sort the customers by name, filter all the customers who are not from London, stuff like that. And then it's really useful instead of just writing out the whole function. And I don't see why it should make testing harder. I mean, if you really wanted to, you could test your lambda function separately by assigning it to a variable, or but you could also test the code that uses the lambda. So it's really the same as global functions. Okay, the one thing I want to say about API design is that lambda functions really make it easier to design STL-like algorithms and code. And what I mean by STL-like is that you have a bunch of templates and lots of functions taking in other functions. And that used to be hard to use. I mean, count if, sort, for each, all these algorithms from the STL, they're really useful and simple if only you have the function. If you already have the function that you want to pass into that STL algorithm. So now, with lambda functions, you always have the function. It's just a matter of typing out the rectangular brackets and you have a function right there. You don't have to go to the global scope and declare functions for this. And it also applies to your own APIs. You should not be afraid anymore in modern C++ to declare a function which takes in a function, or something that looks like a function, or a function that returns a function, or a function that takes in a function and returns another function based on that function, or functional stuff like that. Just a couple of really trivial examples here. Suppose I want to simulate the Windows API for enumerating all the open windows. And so this API takes in a title of a window that I'm looking for, and the callback, which I want to invoke for each window that matches that particular title. And so again, this should not be scary to C++ developers once you have lambdas. This callback parameter can be a template, and then you can pass in a function if you already have one. You can pass in a function object, or you can pass in a lambda. It's really flexible for everyone. And in most cases, when you end up using this enum Windows function, you'd probably use a lambda that does something with the Windows returned. And the second example here is maybe you want to customize the sort function from the STL with your super fast sort algorithm. And again, sort requires a comparer that says which element is bigger than the other. And again, this can be simply a template, and then you can work with functions, with function object, and with lambdas. You're not discriminating against anyone, and this is much more useful than using function pointers directly, because function pointers, in many cases, are only compatible with functions, and not anything else. There is one exception to this, which is why I've mentioned function pointers, which is that stateless lambdas, lambdas that do not capture anything, are convertible to function pointers. And this is a really useful feature which makes interoperability with older technologies easier. So you can take a function that doesn't know anything about templates or lambdas, like read file x from Win32. This is a function that takes a function pointer as a parameter. But if your lambda function does not capture any external state, it is convertible to a function pointer. So you can pass in a lambda. So in this case, read file x, its last parameter is a function pointer, but I can pass in a lambda function, and it does compile. I think it only compiles in Visual Studio 2012. Again, there was a matter of the standard advancing, and there's different interpretations of what implementing lambda function really means, but it is part of the standard. So a standard compliant compiler should be able to implicitly convert a lambda function, a stateless lambda, to a function pointer. So you can use this with Windows API. You can use this with older C-style APIs. For example, the C standard has a function called qsort, which is an implementation of quicksort. And it doesn't know anything about templates and iterators, so it takes a function pointer for this comparer that tells which element is bigger than the other. And so again, you can use this with lambda functions. You shouldn't really write any global functions if you have an API that takes a function pointer. This will work with lambda functions as long as they don't capture anything. This is a really useful feature. Probably the most useful feature in C++ 11 in terms of how we change our code and our API design. Okay. So the next thing we're going to talk about is, I've already told you all this. The next thing we're going to talk about is R-value references. And this, I mean, it's a very important feature in C++ 11, but you only tend to see it once or twice in your application. And so I'm going to explain the motivation here and maybe give you a little more background than is necessary. But there is something at the end of this that will make this worthwhile for you, I promise. So, and R values and L values, a reminder. L values and R values are formal terms used in the C++ standard for declaring the type of a particular memory location or a particular expression. So basically, L values are values that have a name and can appear on the left-hand side of an assignment expression. For example, if I have a variable named x, then x equals 42 is a legal expression because x is an L value and it can appear on the left-hand side of an assignment expression. Everything else is called R values. For example, if x plus 2 is not an L value, it does not have a name, and I cannot assign to x plus 2, and so this is illegal. And I obviously can assign 42 to x plus 2. And similarly, x plus plus, the post-increment operator, this is also illegal. X plus plus is an R value. I cannot assign to it. It cannot appear on the left-hand side of an assignment expression. Another couple of examples. If I have a function that returns a reference or a function that returns a pointer, these are, in certain situations, L values. For example, I could take the value that foo returns and decrement it, because it is an L value. It can be modified. Even though it doesn't exactly have a name, it can be modified. It can appear on the left-hand side of an expression. And I can also do stuff like dereference whatever foo returned, which would produce a reference. And again, this is something I can modify. A dereferenced pointer is an L value, even though it doesn't exactly have a name. And so once we have these terms, let's see why we should care. So there is this one big observation here, which is that R values are usually destroyed pretty quickly. And if your R values are integers, then, I mean, no one really cares when integers are destroyed. But if you're working with large objects, then this observation can provide some opportunity for optimization. For example, suppose I have this function which can accept anything. Just, you pass in whatever. If I call this function with a std vector of int, initialized like this, then this thing over here is an R value. And it's going to be destroyed as soon as the function returns and stops using this variable. Or if I have a couple of matrices, and I'm adding them. I have an operator plus for my matrix plus. This thing will return an R value, a temporary matrix. And I can pass it into this function, but the result is going to be destroyed pretty quickly after the function returns. So the opportunity for optimization here is that if I have a function that knows it's taking in an R value, it might be able to optimize differently than when it's taking an L value. But the current C++ standard, the previous C++ standard, does not have any way of telling whether I'm passing in an R value or an L value. I can declare a function like this, and I cannot inside the function determine whether P is an L value or an R value. And there are situations where this is important. And one example is this. Suppose I have a vector of strings, and I'm pushing back 100,000 strings into that vector. Always the same string, hello, const char star, hello. Now, first of all, this thing over here, this pushback, will allocate a temporary string, right? Vector pushback takes in a string, and what I have is a const char star, so there will be a temporary R value string allocated for every pushback call. And these strings are allocated, passed in, and destroyed as soon as pushback returns. These are R values, classic ones. And so I'm going to have 100,000 strings allocated over here and copied inside the vector, right? Every pushback allocates a string, copies it inside the vector, and then the original string goes away. Not super efficient, right? The second thing here is that vectors, they grow over time. Vectors are dynamically allocated arrays, right? So I push back some elements, the vector gets out of room, and it doubles its size. When it doubles its size, it has to copy all the strings from their previous location to their new location. So I'm going to have even more copies in this process. And again, these two situations are really ripe opportunities for optimization. I want to somehow express the fact that pushback takes in an R value string, which is temporary, and it's going to die very soon. Or when I expand the vector and I have to copy the old elements to their new location, I want to somehow express the fact that I'm not really copying stuff, I'm moving stuff. I'm moving them from their old location to the new one, not copying and then destroying. And this is what R value references enable. So these two ampersands over here is the new C++ 11 syntax for R value references. And this is really a very complex feature, but you usually only need to scratch the surface for your own classes. And this is what you have to do for your own classes. So suppose we have this myArray class. Actually, you know what? Let me show you an example in code. Okay, so what I've done, instead of myArray, I've developed my own string class. Everyone needs a string class, right? So my string class is called lamestring, and it's got a char pointer and a length inside, and I have the standard suspects, a constructor from const char star, a destructor, a copy constructor, operator equals, and a couple of additional operators which we don't really need right now. But the important thing to note are the copy constructor and the assignment operator. So, I mean, this really isn't new. My copy constructor simply duplicates the other string's buffer and copies over the other string's length. So this is a copy, of course, and stirdup is the function that does the copy for me. And my operator equals is pretty similar. It will delete my storage. It will copy over the storage from that other string, and then it will copy over the length from that other string. Make sense, sort of, right? I do have this little bug over here that I allocate memory with stirdup and then delete it with the delete operator, which really isn't quite legal, but let's ignore this particular aspect for now. So in this copy constructor, for example, or in this assignment operator, there is an optimization opportunity if only I knew that other here or here was an R value. What could I do if I know for 100% that other is an R value instead of copying stuff over? What's the optimization opportunity we have?
Just reference.
Hmm?
You can just reference it.
Just, move stuff over, right? So I don't have to duplicate the buffer, right? I could just move over the buffer to my own string. This is the key here. And this is what you really have to do with your own classes. I mean, R-value references are a very big feature of the language, but for most of us, it only means that you have to be aware of this particular optimization opportunity. So if I know that other over here is an R value, then I know it's going away very, very soon. And so instead of copying it over, I can just take its state, move it over, and leave the other object in an invalid or empty state, if you'd like. So instead of duplicating stuff, I can just move stuff over. And so this is what it looks like. I have a couple of versions of this lame string. This is the first one, and this is the other one. Lame string improved. And I have both here, so I can compare their performance, of course. And so lame string improved has two new functions over here. This is the move constructor, and this is the move assignment operator. These are two new functions that you might have to write for your C++ classes. So we have copy constructors and assignment operators, and now we also have move constructors and move assignment operators. Nothing really new here. Let's take a look at the operator, the assignment operator over here. It takes a double ampersand, which is an R value reference. So when this function is invoked, the compiler is 100% sure that other is an R value. But it's not passing a copy of that R value, it's passing it in by reference. So this is an R value reference. There hasn't been a copy yet, and now I have the opportunity of making a copy if I'd like, or optimizing for the case other is an R value, which is what we're doing here. So if other is an R value, I'm stealing its state. I'm moving its internal state over to me. So chars equals other.chars, length equals other.length. This is the stealing part. And then I'm leaving the other object in an empty state. So I'm nulling out its chars and length fields. And this will ensure that, of course, the previous state does not get destructed. So when the other object dies, and this happens very soon, it's an R value, remember? So when other is going to die, it's going to die in an empty state. It's not going to delete anything. And its state has just moved over to me. And so this is essentially what you have to do. I mean, if you know that you have a class that stores some expensive internal state, which takes time to duplicate, like this string here, or an array class, a container, something that owns a database connection, any expensive resource, really, then instead of copying, you have now this opportunity for moving stuff, for stealing data from another object, which is going to die anyway, and then leaving that object in an empty but sort of valid state. So it doesn't crash when it's getting destructed. It just has to get out of the destructor safely. So this is the operator equals, and this will happen when you assign stuff when the right-hand side is an R value. But there is also the copy constructor or the move constructor, which is a similar optimization opportunity. I might construct an object from an R value, and I don't want the copy to happen. I just want the stealing to happen. I want to take the data from the R value, move it over to my object, and leave the R value in a potentially invalid state. So theoretically, I could have this whole code over here just duplicated in my move constructor. But I mean, we don't like duplication so much. So the other thing I could do is just say this equals other. And this sort of makes sense from a syntactical standpoint, because Other is an R value reference. It has this the double ampersand over here. And then this line will probably invoke the move assignment operator, which also takes in something that has a double ampersand. And that's unfortunately not really the case. The R valueness of a certain memory location of or a variable was defined on the slide. An R value is something that doesn't have a name and doesn't have a memory location to which I can assign stuff. But other has a name. I mean, it's called other, so it definitely has a name. So this is a weird situation in which other refers to an R value, but it is not an R value. It refers to an R value, but it does have a name, so it itself is not an R value. And so if I write this thing, the assignment operator that's going to be invoked is this assignment operator over here, which is the standard copying assignment operator. Because again, other is not an R value, so it's an L value, and we have an operator that works for L values, it's this one over here. And the one that works only for R values is not applicable. And so this is why the original code was this, move other. Now move sounds really magical. It's just a standard library function. And what do you think it does? So we have this problem of something that is not itself an R value, but we know it refers to an R value, so we somehow want to turn it back into being an R value, so it works for our purposes. So how could this magical move function accomplish this? Here's the question. Move of other, this expression over here, is it an R value or an L value? It sort of depends on what move returns, but could it be an R value? It doesn't have a name anymore, right? Move other doesn't have a name, doesn't have an assigned memory location anymore. So the move function, all it really has to do is return whatever you passed in. It only has the effect for the compiler of making something that is an L value appear like an R value. It just takes something that has a name and returns something that no longer has a name. It's the same something, but from the compiler's point of view, it no longer has a name. So this is C++, I think, at its finest, where you have to really understand how the compiler thinks in order to do something useful with the language. But again, I think this move thing, you get used to it at a certain point. It really doesn't do anything, it doesn't move anything. It doesn't affect the object whatsoever. It just takes in a parameter, something that could be an L value, and returns something that looks like an R value to the compiler. And so in this situation, it will take this other thing, which refers to an R value, and return something which again looks like an R value, and then the compiler can call this operator down here. Now, how significant could this possibly be? I mean, suppose we're really calling this move constructor and this move assignment operator, which really are more efficient, but could this really make a considerable difference on application performance? This was a rhetorical question. Yes, I mean, yes it can. We're not copying as much stuff as we used to. And this is a local optimization, so basically, if you are developing a string class, then you have to do this for your string class. If you're working on something that wraps an expensive resource, this is where you use this optimization. But then you benefit from it all over your application. Whenever you have to move stuff around without copying, you just save a lot of time. And so I have this benchmark here, which does the following. It's essentially what you saw on the slide. It creates a vector and pushes in, well, a little more than 100,000. This looks like 10 million strings. In the first case, I'm using len string. In the second, len string improved. So the only difference is whether we have move semantics, whether we have a move constructor and a move assignment operator enabled for these classes. And I'm just timing the loop. Now, there are two potential optimizations here. The first, when I'm inserting strings into the vector, I have a temporary string created from the const char star. And that temporary string is an R value. And it has to be copied to its true location in the vector. But instead of being copied, it can be moved, because it's an R value. So no need for a duplicate. So we're allocating twice as many strings in this version than in this one. The other place where we have an optimization applied is inside the vector class. When the vector class has to grow and reallocate its elements, it creates a copy, it creates a larger array, and then it has to copy elements over from the old one to the new one. This, again, doesn't have to be a copy. I have old values which have to be moved to their new location. It doesn't have to be a duplication, it could be a simple move. And so these two things are optimization that the vector class applies. It has a version of pushback that takes in R value references. And it also has an optimization when it's moving elements from their old location to the new one, where it will call the move assignment operator if you have one. So if you have a class like lamestring that doesn't have any move optimizations, it's going to work, but it will incur a copy every time a move was possible. If you have a class that has move semantics, move functions, then it will use them. And so the difference is pretty significant. The first version takes about 4 seconds, and the second just over a second. This is a toy example, which really just benchmarks this one particular aspect of inserting 10 million strings into a vector, but it is 4 times faster, after all. And this is all thanks to not having to copy so much stuff around. We're not allocating as much memory, we're not deleting as much memory, and we're not spending as much time copying strings from the old location to the new one. So again, from our perspective as developers, as application developers, as opposed to library developers, for us, our value references basically mean that we have to consider classes which have expensive resources inside, like myArray, and simply add move operators to them. A move constructor and a move assignment operator. This is all it really takes. And then if you're using library classes like vectors, lists, maps, algorithms, which can take advantage of move semantics, great. If not, you don't really lose anything. You just added a couple of functions to your class. And again, this only applies if you have ownership of some expensive resource. If you only have an int in your class, then there's not much difference between copying and moving an int anyway. But if you have an expensive resource inside, it definitely makes sense to implement moves. And the compiler has a way of generating moves for you. So basically, if you don't have assignment operators, copy constructors, move operators, move constructors, if you have a plain class which does not declare any of this, you will get move functions from the compiler. So if you have nothing special to do in your move operators other than grab the data from the old object and move it to the new one, then you're set. But if you also need to do some customization, like in this example, null out the other object's contents, you will need to implement your own moves. So the stuff that the compiler generates for you is basically only applicable if you don't own any expensive resources yourself. You're just wrapping other objects that might. But if you do have an expensive resource like a string, an array, database connection, a socket, a handle, then you have to think about moving stuff and implementing these operations yourself. Just one more thing about moves. Once we have move semantics, once there is this optimization opportunity for not copying stuff when you only have to move it, you should no longer be afraid of returning stuff by value, even expensive stuff, like vectors and maps of vectors to other vectors, huge objects really. You should not be afraid of returning these big objects by value because of two reasons. First, the compiler already has, and had for years, C++ compilers had for years, an optimization called RVO, return value optimization, which basically means if you have a function that returns something by value and you're assigning it to a variable in your code, there doesn't have to be a copy. The function can use that target location as its own. So there doesn't have to be a copy when a function returns a large object. But even if the compiler does not use this optimization opportunity, you can force something similar with move semantics. If you have a function that returns something by value, that is an R value. A function that returns something by value returns an R value, which does not have a name and cannot appear on the left-hand side of an assignment expression. And so if you have a function that returns a large object by value, and you assign it to a variable, and you have a move operator equals, or a move assignment operator, or a move constructor defined, there will be no copy. It's again the same situation we had with the vector. It's going to take whatever the function returns and move it over to the new location. No copies. So we really should not be so afraid of returning stuff by value anymore. And again, compilers used to be able to optimize this in some situations, but once your expensive resources have move semantics, you can just return stuff by value without fearing the consequences. Of course, again, you still have to verify that you have move semantics for everything. For example, standard library classes like vectors, map, lists, they all have move semantics enabled. And the elements inside, if they also have move semantics enabled, then these containers can optimize even further. If you're using some third-party library, some custom classes that drop expensive resources, you should check out if they really support moves. You should see if they incur a copy when you return them by value or not. But it is definitely possible now to write C++ code that returns stuff by value. You don't have to think about who allocated that memory, who's going to free that memory, am I passing that in by reference or by const reference. You can return stuff by value all over. The other thing you can do with move semantics is pass objects by value to their final destination, which I call a sink in this slide. So a sink basically is the final destination of an object, which will take ownership of that object, and it's not going to go anywhere from there. So again, you can pass stuff by value to sinks, to a function that is going to store that value in its final destination, because it can use move again. It doesn't have to copy. If I pass in something by value, that's applicable for an R value constructor or for an R value move assignment operator, and I can move that parameter to its final destination without a copy. And this is something that's useful because you have a bunch of classes in the standard library, for example, which are not copyable, but they are movable. You cannot make multiple copies of them, but you can move them from one place to another without using references and pointers all along. For example, SD thread, the thread class from the standard library. By the way, the thread class is also part of C++ 11. So the thread class cannot be copied. It does not have a copy constructor. It does not have an assignment operator. It really makes little sense to copy a thread. But it does make sense to move a thread object from one location to another. You might have a class that stores a thread object inside, and then you want to pass that thread object to another class, to its final destination. So again, move makes sense, copy does not make sense. There is an underlying resource, which there is only one instance of, but it is possible to move that whole thing from one place to another, but not to make further copies. And so if you have classes like this, as well in your code, it might make sense to disable copy construction and standard assignment, but still enable move construction and move assignment operators. It might make things easier for you, might make things easier for people who use your classes if you have move enabled for these kind of scenarios. Again, there's a bunch of examples in the standard library, and I hope to have time for at least one. further in the slides. I have a couple of additional language features which I am not going to cover right now because I do want to show you the smart pointers from the new standard library, which were also added in C++ 11. But just to mention the new features, and you can definitely look at them later, there is a feature called deleted and defaulted functions, which is syntax you can use to say this function does not exist. It is useful for functions generated by default by the compiler, like constructors and assignment operators and destructors. You can say this class should not have a destructor. And it's pretty similar to marking these things as private and not providing an implementation, which is what you could do in previous versions of C++, but it is safer and it produces better compilation errors. It doesn't say, hey, this thing is private, or hey, there is a linkage problem. It says this function was explicitly not provided and deleted. So this is useful. You can check it out later. Mostly applicable for compiler-generated functions, where you can say, I would not like this to be generated. The other feature is delegating constructors. This is basically syntax for calling one constructor from another constructor. C++ developers craved for this for years. I mean, this replaces the need for init functions, which you have to call from all your constructors. You can just have one standard constructor which takes a bunch of parameters and call that constructor from your other constructors which take fewer parameters. So this is delegating constructors, calling one constructor from another constructor. Again, the details are for you to complete later. There is a feature called alias templates, which is syntax for declaring partial templates based on other templates. I'm not going to go any further right now, but it's really not very hard syntax. And this is a cool thing that I probably should explain. You have now non-static data member initializers in C++. So we always had the syntax to initialize in place a const static integral field of a class. But this is really restrictive, a const static integral field. In C++ 11, you can initialize non-static, non-const, non-integral fields of your classes inline, like this. Class counter in count equals 0. This is really great. And the compiler basically takes care of adding this assignment to all your constructors. So there's no special magic here, just goes ahead and inserts that initialization into all the constructors that you provide. And again, this works with uniform initialization as well. You can initialize a vector like this. So you could say here, vector v, and then in curly braces, 1, 2, 3, 4. This is really nice and saves lots and lots of typing. So this is now supported in C++ 11.
Prefer to initialize lists and
Again?
this is in preference to initialize lists, which is what we used to use.
Yeah, you can use initialize lists. Yes.
Does it work with forward references?
With what?
With forward declaration, when you want to so if count wasn't there in, but going to throw out my own object.
Yeah. You can use uniform initialization. You can put whatever you want in this curly braces. Okay. And there's a bunch of more miscellaneous features with one notable thing that I'd like to mention, which is raw string literals. There is now syntax, custom literals. There is now syntax for defining your own literals in C++. For example, these could be valid. Break time equals 5 minutes. This is a custom literal, 5min, which the compiler would understand because there is a global function with a certain signature that explains how this literal should be parsed. This is really, really weird, and I believe it got added to the standard because of significant pressure from some data scientists, which really need lots of units in their applications. And so we all now have syntax for declaring custom literals. Visual C++ does not support this yet, and I don't know when exactly they're going to release an update that supports it. It's like their last priority, basically. But you can check it out with GCC or a bunch of online compilers. This is a really weird direction that C++ has taken. So there's a bunch of features, like I've said, minor features in the standard, which you might review later. The one major thing that I would still like to show you is the new smart pointers in C++ 11. And again, this isn't really part of C++, of the language C++, it's more part of the standard library, but they really go well hand in hand because of move semantics and some other stuff that we cover. So the STL now has 3 types of smart pointers. We have a unique pointer, unique PTR, for situations when you are the only owner of that memory. And unique PTR is not copyable, it's only movable. And I'll explain this in a couple of seconds. We have shared PTR if you want to share ownership over memory with other places in your program. So you might have multiple shared pointers to the same underlying block of memory. And finally, we have weak PTR for situations when you have a cycle, a reference cycle, and you want to explicitly break it so you don't have a memory. And again, I'll explain this in a couple of seconds. So we have 3 smart pointer classes to use instead of managing memory directly with new and delete. Well, we might still have to use new, but theoretically, if you write your code from the onset using only the smart pointer classes, you might never have to write a delete statement, theoretically. So let's take a look at these 3 classes. Unique PTR, again, expresses unique ownership of an object. I am the only piece of code in this program, the only memory location that has ownership of a particular block of memory. Unique PTR is movable, but not copyable. So you cannot create multiple copies of unique PTR. You have only one at every given time pointing to a certain memory location. The advantage is, unique PTR is really, really cheap. The size of a unique PTR is exactly the size of its underlying pointer. So you're not paying anything for using unique PTR. And when it gets destructed, it will delete the underlying memory. So you do gain something from having the compiler issue the delete for you, and you don't pay anything in terms of memory utilization, overhead, and similar stuff. And moving a unique PTR, which is supported, only involves moving the pointer. So again, it's super cheap, just moving the pointer from one memory location to another, but the compiler makes sure you don't accidentally have multiple unique pointers pointing to the same thing, and then you have multiple deletes of the same memory location. In terms of syntax, you could have functions, because of move semantics, you could have functions that return unique PTR, which is very useful for factories, classes or functions that create objects. So for example, you could have a function called create, which returns unique PTR of expensive thing. So it returns a unique pointer to that thing by value. And this is only possible because this is an R value, and it can be moved to its final destination. And then I can take this create function and assign its result to a local variable of type unique PTR of expensive pointer, of expensive thing. So I don't have to worry about stars and ampersands in my code in these situations. I can return unique PTR by value. It works like a pointer, but it's much, much safer, and you don't have to delete the underlying storage. By the way, inside the function, you can also work with unique PTR as a local variable. When you return it, it's, again, just a move and not a copy. Another example is storing pointers in containers, which always was a pretty nasty business. If you store a pointer in a container, then who's supposed to delete it exactly, and when's the delete going to happen? With unique PTR, you can put pointers in a container, like a vector of unique PTR of string, and you can just pass in new strings. It's going to sit there in the vector in unique PTRs, and because unique PTR has move semantics, it can be moved. This works even when the vector has to grow. So when the vector grows, the old unique PTRs are moved to their new location, no copies, perfectly compile time safe. So that's unique PTR. Shared PTR is a reference counted shared pointer. So it's much more expensive. There is a reference count inside that says exactly how many shared pointers point to a particular memory location. And this also means that when you copy a shared PTR, you have to increment that reference counter When a shared PTR goes away, you have to decrement that reference counter, so it's more expensive to manage a shared PTR than a unique PTR. On the other hand, it's obviously more useful in certain scenarios. When you really need multiple objects, multiple memory locations in your program, pointing to the same underlying resource. The example on the slide is that you have a class file, which has inside a shared PTR to a file handle. So you could have multiple instances of the class file, which all share the underlying file handle, which again might be useful. And so you can definitely design APIs that take shared PTRs or return shared PTRs if you know that the resource probably should be shared. If you know that there's only one owner for a resource, you can definitely use unique PTR, which is more efficient. I'll have an example coming up. Finally, we have weak PTR, which is designed for situations where you have a reference cycle. You have one object pointing to another, and that other one is pointing to the first one. If you have shared PTRs going both ways, you have a reference cycle, and the memory is never going to be free. So weak PTR is basically a way of pointing to a shared something, to a shared object, without affecting its reference count. So it's a weak pointer because the target might go away, but if I have a weak pointer, I can convert it to a shared one. And here's an example. We have a class employee, which has a vector of shared pointers to other employees, who are the direct reports of this particular employee. And the employee class also has a weak pointer to an employee who is that employee's manager. Now, if I didn't have weak PTR over here, we might have a reference cycle. The manager points to the employee points back to the manager. But here, an employee points directly to the reports, but points weakly to its manager. If I need the manager for any reason, like beg for vacation, then I can take this weak PTR and lock it in place to get back a shared PTR. So this lock function converts a weak PTR to a temporary shared PTR, which I can then use if the target hasn't gone away. If it has, I have an if here that protects me. If I could not lock the weak PTR, it means my manager was already destroyed, and now I'm trying to get a shared pointer to it. And this is not an error, just something that I have to handle if I'm using weak pointers. So these three classes really affect both your API design and the way you store stuff in your classes. And again, unique PTR is for situations where you are the sole owner, and this is typically applicable for most cases when you have stuff you store internally and don't share with other objects, don't return from your functions. You should and can use shared PTR for shared resources, for stuff that you pass around by value. Don't worry about copying the underlying resource, you only copy the pointer around. If you have a function, and this is probably the most important piece of guidance here, which I'll show you in a slide in a couple of seconds. If you have a smart pointer, and you're passing it into a function that's only going to use that smart pointer for the duration of the function, and then return, then it doesn't really make sense. You're not getting anything out of passing a smart pointer to a function which is not going to use that pointer later. So in these situations, if you have a function that takes in something by pointer, by reference, but only uses it for the duration of its scope, doesn't store it anywhere, doesn't pass it to someone else, doesn't use it on another thread, you don't gain anything by using smart pointers. So it's still perfectly fine to use pointers in your code and to use references in your code. Smart pointers do not mean that every function has to be rewritten. You have a bunch of perfectly valid functions that takes pointers, that take references, and you should keep them that way. You should not make them more complex by deciding that you really insist on passing in a smart pointer. It also limits your user. If you write a function that takes a unique PTR, you can only pass in a unique PTR. If you write a function that takes a shared PTR, you can no longer pass in a unique PTR, or a standard pointer, or a reference. So you should not just by default go ahead and Rewrite your APIs to use only smart pointers. Smart pointers are good for sharing ownership and for storing stuff inside your classes, but not necessarily for every API that you ever will produce. And so here's an example. Suppose we have a function calculate tax, which takes in an employee and returns their tax something, the amount of tax they have to pay this year. This function calculate tax really has no reason for taking in a unique PTR, a shared PTR, any sort of smart pointer whatsoever. Because supposedly, it takes in an object, produces an output, returns, and doesn't store that object anywhere. It would be pretty weird if calculate tax implicitly stored another reference to the employee somewhere. And so, in this case, it doesn't make sense to use unique PTR reference, const unique PTR, any other weird combination like that. A plain reference or a plain pointer would work just fine here. A different example is this. Suppose I have a function that has to store somewhere a callback function which will be invoked later when some interesting event occurs. Well, this makes sense for a shared pointer. I'm passing in a shared pointer to a callback function, which is stored somewhere else and is used beyond the duration of the set callback call. So this is a situation where it does make sense to use a smart pointer. So again, the big piece of guidance here concerning smart pointers is that you should not use them by default everywhere in your APIs. Now, I'm a couple of minutes over time already, so I'm just going to show you this slide and its conclusion, and then if you have if any of you would like to hear more, then I encourage you to just ask me afterwards. So in C++ 14, you're right. Or at least that was the intent. And so this particular slide refers to a feature of C++ 14, which is really the major addition to the language, except for some really minor stuff, which is generic lambdas. And generic lambdas are lambda function, which have parameters that are also generic. So this is a lambda function whose parameter is of type auto. And this is a lambda function that you can now use with any parameter that has a foo function available. So this is the major new feature in C++ 14 in terms of the C++ language, and it's of course very, very useful. It means you can use lambda functions with other template functions. You can return lambda functions as templates, and you can even take a lambda function like this and store it in a variable and use it later as a generic function. So this is essentially a template lambda that will work with whatever parameter you pass in, as long as it has the right functions that you use later. There are, again, a couple of smaller features in C++ 14. I encourage you to read more if you would like. And so I'm just skipping into the summary. Modern C++, as I hope you have seen, is quite different in shape and also in essence from the C++ we were used to in the 90s. I started out with C++ in Visual C++ 4.2, and C++ has seriously evolved over that time with lambda functions, auto variables, initializer lists, R-value references. You might read some C++ code that's nothing like the C++ you'd see in 98. Things are looking up in terms of language evolution. The pace is faster. There's going to be a new standard in 2014. There's going to be a new standard in 2017. So they are really working on stuff at a faster pace. And they are also working on the library. And this is really great news. They now have a team working on a file system library. They have a team working on a threading library. They have a team working on a networking library. So there is some potential for C++ here in terms of having a broader standard library, which has more than just containers and count if and stuff like that. So again, thank you very much for staying and overstaying a couple of minutes with me. My contact details are here on the slide if you'd like to follow my blog, Twitter. The slides you have on your memory sticks, and if you'd like a couple of examples which I've shown you, I will put them on my blog as well. So again, thank you, and if you have any questions, please come forward. Thank you, and enjoy the conference.